All right, so in this section, I want to just give us a little brief introduction, and then go through some examples of rigid bodies and what they are and how we can use them in Houdini to make some cool effects. So rigid bodies generally are hard objects that behave like physics, that react to the laws of projectile motion and physics in general. So if, for example, that would be something like a brick or a domino or a dice or glass breaking or something like that. Generally, it's, rigid bodies can shatter. They can break from, go from one object into many objects, or they can just simply be, a cube or something simple that is just falling and tumbling around and colliding with other objects in a way that is, that mimics the laws of physics in the real world. Doesn't really include things like soft bodies, so you wouldn't be simulating pillows or, cloth or anything using rigid bodies. Rigid bodies are they're rigid. And, but there are some really great solvers that are specifically designed to deal with that kind of thing in Houdini. Namely using the rigid body solver, which also contains the bullet solver. And the bullet solver is, generally speaking, the main, it is like the main solver that is used to do a lot of physics simulations. And I think it's even used in video games. If there's some sort of physics in video games, it's performant enough to work pretty close to real time, if not in real time, depending on how much you're throwing at it and how efficient you're being with the things that you are throwing at it. So I just wanted to walk through a couple examples that I've come up with that sort of will just show a little bit of the basics of how to set up some forms of rigid body simulations, how Houdini is dealing with geometry when it's actually creating these collision hulls and everything like that, and then how we can just expand it a little bit further using something called the multi-solver and a SOP solver to just sort of kind of add a little bit more behavior to it behind the scenes. So to get started, let's just throw down some test geometry. I'm going to throw down the squab test geometry. So if we hit that, we get this nice, squid squab thing looking right here. I just got to save this. And I'm also using my my quad layout that I set up in our intro to Dynamics. So if your interface looks different, you can feel free to follow along using that, but I will be using the quad layout for this. Just makes it a little bit easier for me to demonstrate some of this stuff. So again, I've got my squab here, and what I want to do is I'm just going to turn it into an RBD object. First thing I'm going to do is I'm just going to jump inside. I'm going to lift it up a little bit. So I'm just going to hit this translate middle mouse button, bring it up like that. And then I want to drop it on the ground plane. So we're going to need a ground plane eventually. But the first thing I want to do is just turn it into a RBD object. So I'm just going to go up to my shelf up here. I'm going to go to rigid bodies, and I'm going to select RBD hero object. What that does is it creates an autodop network for us. And it does a couple other things in the test geometry. Let's just dive in there real quick. It creates a rest attribute for us that basically stores its initial position, and then it'll just re-import whatever's happening over in our DOP network or simulation. If we just jump into the simulation, you can see that it's created an RBD object for us, and a merge, which we're not really quite using yet, but then a rigid body solver, which is set to use the bullet engine like we were talking about, and then it added some gravity for us and an output. So if I just hit play, you can see that the squab falls down, and nothing really happens after that because there's nothing for it to collide with. So I'm just going to go back up to my collisions tab and just add a ground plane. So now this infinite ground plane it will collide with. If I hit play, you can see the squab falls down and comes to rest on the ground like so. This geometry really lends itself more to a soft body simulation, but it has a lot of little nooks and crannies, like legs that legs where objects could pass between, and like these tentacles at the beginning as well. Which we'll talk about in a second. So I think one of the main things about the squab that it would help me illustrate this point is if I go over to my RBD object here and select this geometry and show under, let's see, if I go to the collisions tab, and then I go to bullet data, I can, because I'm using the bullet solver, I can look at the guide geometry. It's actually going to show me what the collision hull looks like. So if you see here, it says convex hull. If I click show guide geometry, you can see that it is actually this is the geometry that's actually being collided with the ground. So if I drop that on the ground, you can see that it's really just calculating a shrink wrap of that geometry, like so. So if I were to do something like add a whole bunch more cubes in here, we'd have to come up with a way to get around that. So I'm going to just do that to sort of illustrate what I'm trying to say. So if I go over here, let's just create some more geometry that we can drop on top of this. So I'm going to just throw down some more test geometry. And this time I'm going to choose the pig head, like so. And I'm just going to jump inside the pig head and bring him up, him or her, not quite sure. Bring him up to about so. About like, looks like 3.5. Just want him above the squab so I can kind of drop him and have him interact with the squab. So here I'm going to create a bunch of cubes out of him. So let's just do a let's do a points from volume. So, and this points from volume is just going to scatter points uniformly throughout the inside of this object. I will also add a box in here, and I'm just going to clone the box onto all these points. And a trick that I'm going to do is I'm actually going to make the uniform scale of the box equal to the point separation on the points from volume. And that's actually going to create like a very non-overlapping grid, kind of like, you know, kind of like the first steps you would take if you were trying to create like a sort of voxelized Lego look. So I'm just going to paste the relative references here onto the box. So our box now is at the, let's see, you can see it here at the origin, but when I do a copy to points and copy the box onto these points, we get this voxelized grid like so. And then when I change the point separation, it dynamically scales the cubes to match. So they're always sort of just enough cubes in there, and they're all kind of, you know, just butting up right next to one another. So here, let's turn this also into an object in our simulation. So I'm going to hop back out here, and let's go back to the rigid body shelf. And I'm going to choose, again, an RBD hero object. Now, this isn't going to work the same. This is asking me to select objects for RBD hero object. Okay, well, I'll select the pig head. And it's now my timeline, because I was on frame 71, it turns orange. It's basically saying that our simulation's out of date. So I got to go back to frame 1. And you can see it looks like I didn't raise the pig head up high enough, so I'm going to do that right now. I'm just going to hop inside here, go back up to my pig head, and let's just bring it up to something like 5.2. Let's just call it straight, just an even 5. So now this isn't going to work, and I'll show you why, because I'm going to drop these two. I mean, it does work. Technically, we've told it to do this, but we want all these different cubes to sort of fall apart and each act as independent pieces. Well, that's where packed geometry comes in. So if I actually go into the auto dot network, you can see that it's also added in our pig head test geometry. I'm going to delete that. We're just going to back up a little bit and do this the correct way. So inside here, it's also added a rest and a dop import. We don't need those. We're actually going to go about this a slightly different way. So instead of choosing the RBD hero object, I'm going to actually select this and choose RBD objects. And basically what it does here for us is, if we look over at our simulation, it's an RBD packed object. And then if we jump inside our test geometry here, you can see that it's done a similar thing. It's added a rest attribute to store the initial position, but then it's set up a thing called packed primitives. And if you look here, it's created a name attribute. We can see our name attribute over here. It's prefixed by the word piece, and then it's just simply numbered all of the 10,000 pieces that we have inside of this pig head. It has given them a unique name, and when you have a unique name and then you put that and then you pack that geometry, setting up packed geometry, it will it's basically at that point giving Bullet something that it can understand as what individual pieces are, and then it is referencing them in a very efficient way in memory. So if we'll show this. If I go up to this copy to points, where we're just simply copying boxes onto points, and I middle mouse click, you can see we've got 82,336 points, the primitives, different number of primitives, and then we've got all sorts of vertices, polygons, etc. Now after the pack, what it's done is it's actually stored the cube as like an instance in memory. So now we only have 10,000 points, 10,000 primitives, and etc., etc. So it's a very efficient way of storing the information. You can see like it looks like it's actually trying to smooth all those normals. You get this weird shading. I'm just going to add a normal up to our box over here, just because I find it a little bit more pleasing to look at when everything's got a nice hard edge, especially if I'm working with cubes. So now let's just play back and see what's going on here with our simulation. I'm going to just open this up a little bit and just bring this down, and let's just hit play. You can see it's chugging through. That's because it's got to think about all those little pieces as separate individual cubes. So now our squab has collided with the ground, and our pig head is now being broken apart into 10,000 little tiny cubes that are all interacting independently with the environment. Just to make things go a little bit faster, I'm going to go up here and increase my particle separation on the pig head to something a little bit lower, just so we get fewer cubes. So let's just bring the point separation back to 0.1. And you can see it's recalculated that. And now when we middle mouse click over our packed prims, we're only dealing with 2,000, which is still a decent amount, but should just run a little bit faster. So I'm just going to go back to frame 1 and go over to our sim. If I select a node over here in our sim, then we'll be basically, it updates the viewport to be inside the sim, so that's good. Now if I click play, you can see it's clipping along much faster, and we drop the pig head on the squab, and all these cubes come flying out, and eventually they will all sort of kind of come to rest as they are done doing their thing. But one thing to note that is happening right now is we're getting this weird thing going on because of that collision geo. Remember how we had looked at our guide geometry on the squab? You can see that none of these pieces from our RBD packed object are actually going through this hull. And it would be really nice if on here we could get these pieces to kind of fall into all these convex cracks. Like if I just let's just go back over here to the squab. Like, so if the cubes could like fall between these different tentacles and go between the legs, say, and just kind of fall into every little kind of nook and cranny of this complex geometry. So there's a way that we can do that. And we can do that by actually cutting. Essentially what we're going to do is we're going to cut apart this geometry into a bunch of different little pieces, and then make a convex hull out of each one of those, and then kind of stick them all back together so they behave as one object, but but Bullet is able to compute a bunch of little convex hulls for it. So basically concave versus convex. Convex is more or less if you look at our test geometry here, at our collision geometry, convex means that there's really no indented or like inwardly curving surfaces on this. Everything is curving outward. So you get no sort of like indentation or any detail in that regard. So I mean, there are other ways you can add you can create a convex hull per set of connected primitives, but we only have one connected object here. So if we let's just delete out our RBD object and start over, because there's a shelf tool that will help us set this up. So I'm going to delete I deleted that RBD hero object out. I'm also going to jump into the squab, and I'm just going to delete this because we're going to just have the shelf tool do a different thing for us. starting up here. So I'll oftentimes just delete out things that the shelf has done for me and try a different shelf tool if it isn't working. So if we go back up to our top level, I'm going to select the squab, and then I'm going to go over here and then choose the RBD convex proxy. So I give that a click, and it's thinking about it. And now if I dive into the test geometry, you can see that it's actually it's creating a name attribute. And then what it's doing is, let's see, I'm going to just lay this out a little bit better. I'm going to grab these guys, move it off to the sides. So it's thrown down this node called convex decomposition. And what convex decomposition tries to do is it basically looks at the geometry, scatters points, kind of breaks it apart into into convex hulls that represent the geometry a little bit more closely than that very generic convex geometry we had before. Then it does the same thing that we did in our other with the cubes in our pig head. It assembles them, it creates packed geometry out of each one of these convex hulls, and then creates proxy geometry for us. And then here down at the bottom where it says transform high res, what this special node does is it takes an import from the DOP network, and it uses that as a guide to transform each individual piece independently. So now if I go over here and let's just lay out these nodes. So now we've got our test geometry squab right here. It is now an RBD packed object. It's no longer just an RBD hero object. It is actually packed geo, just like our cubes on our pig head. But what's going on with it is something a little bit different. You can see here it is creating a convex hull per set of connected primitives. So because we created this name attribute up here, it's treating all of these different pieces as one piece. Because you can see down here, once we decompose it into its convex pieces and then assemble it into packed geometry, we're not overwriting that name attribute. We just got one piece here, so to say. So because the bullet solver relies a lot on these names, it takes a little bit of getting used to, but essentially you're going to be using a name attribute to kind of tell the solver how you want your simulation to be partitioned, because all of these convex pieces are essentially named the same thing. They are all assembled into just one primitive. So if I middle mouse click here, you can see there's one primitive. But our test geometry, our RBD packed object is actually creating a convex hull per set of connected primitives. If I untick that, actually, let's just show the guide geometry. You can see that it is actually created, it's creating separate collision hulls for all these pieces, and they're sort of stuck together. If I untick create convex hull per set of connected primitives, it goes back to what we had before, basically a general convex hull for all the geometry. So now I'm just going to turn off showing guide geometry, and we'll just play this back a little bit. So making sure something over here in my DOPNet is selected, I'm just going to hit the play button, and we'll see what we get. I'm just going to pause it. I'm also going to turn on hide other objects so that we can just stay focused here on our simulation, and hit play. Now you can see that all these cubes are crashing. They're going between all these tentacles. They're going around all the legs. They're really just getting in there and getting real, you know, which is what we're after. So that's just like one of those things that isn't, I found, like, prior to me understanding how this whole setup works with Bullet being a very optimized, very fast solver, it's taking shortcuts essentially in order for it to work very well and very efficiently. But with those shortcuts that it takes, you run into things where you got to get around it to essentially you got to hack it to get it to see the geometry in the way that you want. So if your sims aren't working out right, just a good thing to note is, you know, you can come in here, check out what your collision geometry is doing, and if it's looking bad, you can just re-explore the shelf tool, try one of these other proxy options, and get better collision geometry. So that's sort of like just a basic simulation. What I want to do now is I'm going to just, let's just go over here, and I've got all this right here. I'm just going to select all this stuff and hide it, and we're going to just kind of start over. So now what I want to talk about is how we could maybe emit a bunch of cubes into a scene and have them sort of just, you know, if we wanted to create a pile of cubes that was sort of coming out of, like, you know, I don't know, a faucet or something, we can kind of do that as well. So let's create our emitter. This is where we're going to get into using the multi-solver. And the multi-solver sounds super confusing, but it's really, I mean, it sounds intimidating. I thought, honestly, I was like, a multi-solver, whoa, I don't want to deal with it. First time I heard of it. But really, it's not too complicated. It's pretty basic. So let's just go and throw down another geometry, and we're going to call this our emitter. And I'm just going to jump inside of it, and we're going to create a sphere. And we're going to just scatter some points inside the sphere that are going to tumble onto we're going to scatter some points on the sphere, clone boxes onto them, and those boxes are going to fall onto the ground. So let's do an ISO offset. And inside the sphere, that just kind of creates a volume out of the sphere. We can scatter points throughout. So we'll throw down a scatter node and like that. I'm just going to force the total count to 10. So we've got 10 points here. Just going to hit the D key and make it so that we can, just for the video, so that you can see the points a little bit bigger. They're a little bit bigger when I do this. So there we go. And now I'll just throw it on a box, and we'll just get that box to be a reasonable size. I'll just maybe dial it back a little bit like so, and a copy to points. Copy to points, wire the box on the left. The box on the left will copy into the points on the right. And we highlight that, and we've got our boxes like so. Nice. So I think that we could use this as our emitter, but every single frame, it's going to be more or less emitting the exact same pattern. We can randomize that by coming down here on our scatter node and selecting a global seed. You can see if you change the global seed, it just changes that scattering pattern. And what we want to do is just vary this every single frame, because we want it to emit these cubes into our scene every single frame. So I'm just going to go up here and type in @frame into our seed, and you can see that now as we scrub, our global seed is changing, and it's changing every frame, which is great. So now what we got to do is we want to get this into another sim. So I'm going to actually go out here and create a new sim, because we had this other example over here. If I start using the shelf tool, it's going to start putting my this new stuff that I'm creating into this old sim. So this is just kind of a tricky thing to this is sort of a trick to get the shelf tools to start putting things in the right places. You can just create a .NET yourself. So we're just going to do that. I'm going to throw down my own .NET network like this, and then if you look down here, it's got our there's this little menu where you can select which sim you want to be like dealing with right now. And if you look down here, we've got our auto network. The checkbox is on that one. That basically means that any shelving that I'm doing is going to shelve the tool setup into that network. I don't want that. I actually want it to go into my .NET that I just created here. So I'm going to just call this my emitter sim. Emitter RBD sim, something like that. So you can see down here, it's the emitter RBD sim. Cool. That's the one I'm working on. That's the one I want to shelve. That's the one I want my shelving tools to affect. All right. So now with this all set up correctly, let's just go to our emitter, and we're going to turn it into RBD objects. So click that. And over here, I've got the wrong .NET displayed. So I'm just going to select our RBD emitter sim. So here now we're in our emitter. We've got our emitter right here. And if I dive into this SOP geo right here, you can see that it's done the same thing. It's set up at rest for our rest position. It's done the name attribute for us. You can see over here, we've got our pieces, and it's assembling them into packed geometry and throwing them in our import, or into our network, which is then being re-imported back into this scene. So basically from here, if you look at our emitter, it is pulling in the first input of our import. So that's what this means. The SOP input path basically means look over at this import, grab the 0th input, or the first thing coming into it, and that's going to be our path. So essentially it's looking at whatever's leading into this guy, bringing it over into this network, And then right here, this node is actually set to grab the objects created by this emitter. So it's just sort of like a little handoff. This is looking basically at this wire right here, pulling that info, sending it back out. Now, if I hit play, and you can see that we have no gravity in this situation because we set up our .NET on our own. So it didn't by default give us gravity. I'm just going to throw that in. So I'm going to hit tab, type gravity. I just like to wire gravity in basically at the bottom because I want everything to be affected by it. And hit play and those boxes fall down. Cool. Let's just give it a ground plane to collide with. And again, I'm going to throw a normal over here. So that's inside my emitter object. I just want to add a normal to my box because I don't really like the way this looks. It makes more sense to me to look at something that looks like that. Nice cusped edges. So now with that, I just want to throw down another ground plane. So I'm just going to go up here to collisions and select ground plane. And it has added that in here for us. You can see it's wired that up for us. And if I go back up here, it's, Houdini just likes to throw these guys kind of almost, it looks like it just arranges things diagonally. I like to keep my setups sort of vertical. So I'll put my .NET, or I'll put my .network on the bottom like so. Just have all the things that are sort of related vertically aligned with one another, at least when I'm working on multiple setups inside of one file. So now when I click play, the cubes fall and they land, and that's great. But we're not getting any more, we're not emitting actual boxes from this scenario. So this is where something called the multiple solver comes in. And to illustrate how that works, I'm just going to bring this up a little bit. And we're going to just sort of focus over here on this, on our sim. So the multiple solver. We're going to need to, the multiple solver is what you would use when you want to combine two different types of solvers in Houdini. And really all we're trying to do is add these cubes back into the simulation every single frame. So the way you do that is using a SOP solver. A SOP solver allows you to do SOP-like operations, such as cloning objects onto points or just merging geometry together. It allows you to do that inside of DOPS. So in order to actually use a rigid body solver and a SOP solver at the same time, we got to use a multiple solver. So this is how it works. I'm going to hit tab. I'm going to throw it on a multiple solver like so. And I'm going to just actually, instead of wiring my emitter into here, see, I'm not going to create any more objects. I'm just going to get rid of this merge because it's kind of confusing. So this emitter is going into our rigid body solver initially. Well, to get it to work with the multi-solver, I can actually wire our emitter into the left input of the multi-solver first. And then actually, instead, I don't want to have it right here. I'm not going to actually wire this RBD packed object into the rigid body solver at all. Instead, what I'm going to do is wire the rigid body solver itself into this little purple burger thing that's sitting over here on the edge of the multi-solver. So now, instead of wiring the rigid body solver out into the merge, we're just going to take this cord and snap it into the multi-solver. So essentially, having the emitter flowing into the rigid body solver and then downstream is the exact same thing as having the emitter flowing into a multi-solver that is attaching a rigid body solver to the situation. So if I hit play now, we're getting the exact same result that we did just 1 second ago when we were actually probably more than like maybe 45 seconds ago, but you know what I'm saying. We get the exact same simulation, but now what we can do is wire more solvers in right here. So what do we want to do next? Well, it was the SOP solver. So I'm going to throw it on a SOP solver. And SOP solver basically just gives you access to something that is very similar to this type of SOPs context out here. So you get all your nodes. Like if you look, you can do modeling and stuff inside your SOP solver and actually have it update geometry every single frame in a way that you would be comfortable with doing over here like you would be doing in SOPs. So I don't know how this got disconnected. I'm going to wire back in my rigid body solver, and then I'm going to wire in my SOP solver. So I'm just going to double click to jump inside of our SOP solver, and you can see we've got these, we've got our dot geometry, we've got these impacts, feedbacks, relationship geometry. I generally don't use these for most things, so I'm going to just drag them off to the side so we're not distracted with them. And right here, what we've got is our dot geometry. Now, in this context, this is a geometry context, just like this over here is a geometry context. So things you're familiar with doing inside of your SOPs, with your SOPs, you can also do over here. So all these nodes that are available in SOPs are generally speaking available over here. Now, whether they're going to do you any good in terms of working in the simulation is one thing, but what we want to do is actually merge some geometry together. And basically what happens is at the end of this chain over here, wherever the display flag is set is going to be what is updated into our scene. So since we've got DOP geometry that's being imported into SOPs, this SOPs context that can update every single frame, it is going to be fed back out, and basically nothing's going to happen. So again, if I click the play key, if I click the play button down here, nothing happens when we're inside the SOP solver. It doesn't update generally when you're in here. So if we just jump up one level and click play, we have the same results that we had before. We're basically doing nothing in terms of the SOP solver. So that's just an important thing to note. Like when you dive in here, if you're looking for feedback here, it doesn't really do anything inside of the SOP solver. So basically what I would do at this point is maybe if I'm going to be doing some work inside here, I'll just pin the actual, I'll just hit this pin up here to lock the display to my DOP network. So when I do dive inside the SOP solver, I can play that back. Cool. So what we would do now is we basically would just want to merge in our geo. So I'm gonna throw it on a merge, like so. Or not. Well, I do need a merge, but I also need an object merge so that I can bring this stuff in here. I'm gonna just set up right here a nice little null for myself to grab onto, just because I like to kind of note where I'm going to be moving geometry out. So I'm just going to call this our boxes. I'll call it box pieces. And then over here we've got our object merge. I'm just going to merge that in here. So now in our SOP solver, we're merging in our box pieces, which are, if I untick this, if I unpin this, the display will update inside of our SOPs thing. Now you can see here it is bringing that into our SOPs solver. And now if I merge this together, and then I'll just throw it on an output. Output helps us make sure that it's actually outputting this node, even though I might have another flag selected. But so if I click this right here and then jump back up, now you can see every single frame, it's adding more of these boxes into our scene. Cool. So if, you know, it's looking like it just keeps adding and adding and adding. If I wanted to actually have it sort of stop at some point, I might do something like this. Now, given like how this is very close to the ground, it's sort of piling on top of itself, I actually want to make these boxes just a little bit smaller. So I'm doing something like 0.3, like that. And then I'll maybe just bring this sphere up a little bit higher, just so that there's more room for it to fall and collide with the ground. So I brought the sphere back up to maybe about 0.65, or no, sorry, 6.5, something like that. So now I'm going to go back over here to the into our RBD sim, and let's click play. You can see it's just making cubes, they're birthing, and they're falling onto the ground. So let's say we want it to go for 48 frames, and then we want it to stop after 48 frames. I might do something like this. I'll just jump into the SOP solver, and I will use a I'll just use a null and a switch. So if I just throw down a null basically is going to say this is going to be nothing. So right here, our object merge is merging in our emitter geo, and this null is literally doing nothing. And we can switch between those dynamically using a switch. So I just throw it on a switch node and wire the object merge in here. And then I'll also wire this up over into the nothing thing, so that our second input is the nothing. So you can switch these around if you get it mixed up by hitting Shift R. That'll reverse them. Or you can go and on this list, if you just hit this up button, you can make sure that your object merge is actually the first input. So what we can do here is we can say, if the frame is greater than frame 48, we just switch over to nothing. And the way we can do that is just by writing at frame is greater than 48. And what that means is when we reach frame 48, this will evaluate to true or a value of 1. So now we're below frame 48. It is evaluating to 0 because we are not greater than frame 48. So that will make this evaluate to 0 until we hit frame 48, and boom, then you can see that this dotted line here switches to become solid on the nothing section, and it starts to it stops emitting, and this selecting the input, it starts to select this input instead of the initial merge. So when I go back out here and click play, it emits to frame 48, and then it stops. And we have created a pile of cubes over 48 frames. So that's sort of how you would use a multiple solver to create an emission-like scenario in with Houdini and rigid bodies. So let's explore another scenario now. Now that we've done this, I'm going to just hide. I'm going to grab all these and turn the display flag off. And we're going to do another one. We're going to actually activate particles that, or activate pieces that, we're going to basically activate objects by turning them on and releasing them into the simulation. So let's just create some geometry to play around with. I'm going to throw down another geometry node. I'll call this one, we'll call this, let's say we'll call this the floor. Because what we're going to do is we're going to create a floor, and then we're going to kind of break it apart. So if I go over here and I dive inside here, I'm just going to throw in a box, and we'll just make this box. We'll do the rested on the floor trick, which is copying the Y size and pasting relative reference into the center size, and then just dividing by 2. That gets the box to nicely rest on the ground, and then whatever height I give it, it will always rest on the ground like so. And let's just increase the its size in X and Z to something like 10 by 10, like so. Cool. So now what I can do is let's do this. Let's Voronoi fracture it. I'm going to use an ISO offset, and I will scatter a whole. Well, this will basically create fog volume we can scatter in. So I'm just going to increase the sampling divisions to 50, so it's pretty high res, and then we'll throw on a scatter, like so. And we got all our points scattered there, and then I'll just throw it on a Voronoi. Voronoi fracture will take the geometry in the left input, which is the geometry we want to fracture, and then we're just going to feed the points we created as our fracture cells. So you can see in here points for Voronoi cells. Just wire that in there and highlight that, and we get this nice Voronoi fracture pattern here. So I'm going to, if I just hit the exploded view just to visualize it for a second, you can see that we get all these points. Like so. I'm going to just, on my scatter, it will relax the points. I just want to have them a little bit less uniform, so I'm going to untick relax iterations and then take a look at my Voronoi. And we get some cells that are bigger and some that are smaller. So it's slightly more random. And this is a pretty basic example, so I'm not going to go into too much detail and try and create like some crazy setup here. I just want to kind of go over this example relatively quickly so that we can sort of get just more of an understanding of what the possibilities are inside of RBDs. So I've got my floor. Now what I want to do is create a RBD packed object out of this, because I want all these little pieces to be able to interact independently. So to do that, I could do the shelf again. So I'm going to just throw down a DOP net, because like we did before, I want to have if we go down to the lower right hand corner, I want to have it focus on this new, if we're using our shelf tools, I want it to focus on this new sim. So I'm going to call this, we're going to call this RBD activation sim. So now I'll go down to this corner and I'm going to select the RBD activation sim, grab my floor, go to rigid bodies, select RBD objects, and the sim is out of date. We get this big orange bar because I was in the middle of, I was at frame 131 when I clicked the shelf. Go back to frame 0 and hit play, and nothing happens. That's because there is no gravity, but it is simulated. You can see it's starting to catch from that blue bar that's showing up. Throw it on a gravity, and throw it on a gravity. You can see that all those pieces are starting to fall down. So what I could do to actually prevent that from happening is I could actually deactivate all these pieces and then dynamically reactivate them in SOPs. So if I go up here to the floor, you can see that what it's done is it's done our usual thing, adding a rest position, setting up our packed primitives, and then you know, going into our DOP, creating our DOP network here. Now it looks like, based off of this, it's not this setup packed prims did not create a name attribute, because a name attribute is actually being created by this Voronoi itself. So you can see that we've even though we haven't used this assemble, this name attribute is being created on our primitives here. We've got our piece 0 and so on and so forth. And basically what that's doing is it's grabbing every single face of each one of these Voronoi cells and saying, well, is this face a part of piece 1? Yes. So is this one, so on and so forth. So that's why you get all these when you look at your geometry spreadsheet, when you're looking at your faces, you can see like a whole bunch of them are named piece 0. That's because these are all the polys that go into piece 0. Then when we assemble them, it packs them into points, and then we get one name for each piece. So what we want to do now is after this, we want to add we want to add an attribute that tells it that whether it's activated or not. So I'm going to throw it on an attribute create here, and then now this is one of those, you know, universal attributes that you want to like kind of remember if you're trying to do this type of thing, that the solver, that the RBD solver is going to understand if you feed it into your situation. So if I go in here and say attribute, we're going to create an attribute called active. It is actually an integer attribute just because it's active is either 0 or 1. 0 means it's inactive. 1 means it's true, which means it's active. So by default, if I give this a value of 0, it is going to, if I play back over here, if I select a node over here and click play, literally nothing's happening because we have actually deactivated everything by just having this value 0 here. Put in a value of 1, simulation's out of date, go back, hit play, everything starts falling. So this is where like groups can come in handy. You could actually say something like, we could create a sphere. And what I could say is like, let's just check everything inside of the sphere, and if it's in the sphere, I want it to be active. I'm going to set our default active value back to 0, and then we'll just throw down a group, and we'll just throw this in here, and then I want to actually group points, and I want to group, I don't want to use this base group, I want to use the bounding regions. We're going to use the bounding object and just wire in our sphere. So now you can see that anything inside of this sphere is going to get activated, is going to activate this group. So if I grab this and kind of move it around, see here, I got to grab this sphere, and I'm just going to move this handle around. You can see that these green chunks are becoming highlighted. That is the group sort of indicating to us that those are pieces that are part of the group. I can change maybe the size of the group, make it a little bit bigger. You can see that it grows that selection. So let's give this group a name of something other than group 1, something that makes sense. We'll call this the activated group, and then we can throw down a point. Now the point attribute, or the point SOP, was previously much different, and if you see it in older tutorials, it'll be a lot it'll be in a much different format. But this is the newer version of the point attribute. It's more or less a mini version of a wrangle, which is more of a way of using Vex to do to set some attributes. But I'm just going to use it to basically set any attribute, any of the points that are in group 1. I'm going to set them to active, their active attribute to a value of 1. So I'm just going to wire this in here, and if I go here, I can say you get these different options that you can select from on your Vexpression here. And this doesn't need to be you can make this more complicated if you want to, but really all we want to do is set a constant value. So we're setting a constant value. The attribute we're going to choose isn't position. We're actually going to use a custom attribute, and that attribute is going to be the active attribute. So we're setting the attribute, and it is not a vector. It is actually just an integer like we set up here. So we have an integer active, and down here we're just going to be setting a custom attribute called active that we created earlier to a constant value of 1. And then we don't have to do anything with this down here. Basically what this Vexpression is doing is it's saying whatever's in this field right here, it's going to evaluate to. And then now to make sure it doesn't do that to all the points, we just specify the group we want to work on right here, which is activated. So now only the activated group will have an attribute of 1. So you see over here in our geometry spreadsheet, if I sort by active, you can see that there is now the active attribute is set to 1 for everything in the group activated. Makes sense. So now if I just select a node over here and click play, you see that those pieces only in the center of wherever that sphere were, only those pieces are becoming activated and turning into simulation geometry. Whereas, but the cool thing is that all these other pieces are acting as colliders. You see, when we start to play back this simulation, we get a little bit of, you can see that these pieces on the edge are actually colliding and, you know, kind of rotating out a little bit. So it's not to say that those pieces don't fully influence the simulation. They just aren't, you know, moving rigid bodies, but they are static rigid bodies, basically, at this point. Cool. So now if we wanted to sort of animate our activation, you might think that you could go up here and do something like grab your sphere. Oops. Maybe I'm going to hold down Option, click here to keyframe where the center is. And then I'll go, you know, actually, in terms of what I find to be a better practice, I'm just going to zero this out, and then I like to put this all on a transform. So I'm going to throw it on a transform just so that I know that my animation isn't, I'm not really doing any animation on the original sphere. I like to kind of isolate it to a transform, and then maybe do something like color it green so I know that it's animated. So maybe I'll like go and just grab this translate, move it over here, set a key on the sphere, and then maybe move this back to frame 1 and move it to the left, and then set another key. And maybe I'll make that a little bit longer. Maybe I'll make it 72 frames. So now our sphere is moving across our grid throughout those 72 frames. So now if I look at my activated group, you can see that that sphere is moving and activating all those different pieces. And if I were to move back over now to the DOP network and click play, you can see that it only activates that first chunk. So even though this sphere is moving across, if I just go in here, say ghost all other objects, and maybe I'll just highlight that, you can see it's activating that first part, but it's not continuing to update. And that's because we need to insert this into, it's only instantiating this simulation based off of the data that it receives on that first frame, because the creation frame is frame 1. So what we can do is use another SOP solver to actually kind of achieve this effect. So what I'm going to do is, let's just do what we did previously. So over here in our sim, I'm going to throw down another multiple solver. Whoops. Undo. I don't know what happened there. So I'm going to throw down another multi-solver like this. And we're going to do the same thing. We don't need this merge. Just going to delete it. The merge is if we had more than one RBD object, not necessary. Just going to wire the floor into the multi-solver instead. I'm going to disconnect the rigid body solver from the floor. And then I'm going to take this wire and plug it into the purple area on top of the multi-solver and throw the multi-solver back into the merge below it. Now, if I click play, we get exactly what we had before. Basically, we've just detached the floor from the rigid body solver, put it into a multi-solver, and reapplied the rigid body solver data to the multi-solver. So now we can add more solvers into this multi-solver. Let's add a SOP solver, like so, and I'll just wire that in here. Now, what we can do is we've already kind of done our work here. We've done what we want to achieve here. What we can do is actually just kind of copy this stuff off and paste it into our SOP solver. So let's do that. We've got our sphere that's already animated with this transform, and we've got a group that's being created based off of the bounding region of the sphere. And then we've got an expression that is updating the active value based off of the group. So I'm just going to select these 4 nodes right here, copy them. I'm going to swing over here to the SOP solver, and we're going to double click to dive inside. Don't need to worry about any of these pieces. I'm going to drag them off to the side. Now I'm going to paste in these nodes that we copied from over here and just wire through the DOP geometry. So if I wire that through and put the selection at the end, and let's go back and see what we get. Now when we click play, you can see as our sphere moves through, what it's doing is every single frame, it's doing its rigid body solve, and then the next thing it does is it looks at the sphere, transforms it, looks at where the animation or where this new activated group is, and then sets the attribute expression to active. And because it is more or less just because this group is actually just overwriting pieces that are affected by it. It's not deactivating any pieces. You can see that those pieces that were activated in the first frame have continued to fall indefinitely. But because it's only really changing values on the regions that are affected by the group, it just is essentially turning those pieces on and moving them along, which is kind of cool. So it's really like a way, it's just it may seem convoluted that we have to use like a couple solvers to do this, but it's a very nice and explicit way to basically take something that makes a lot of sense to do in SOPs and allow you to do it inside of a solver with this continuous updating that goes on like so. So what other kind of fun things can we do? We could probably add some sort of force to this. So inside, if we've got our SOP solver in here, maybe what I'll do is I'll actually keep this SOP solver up. I'm just going to drag one of the nodes from this area to the left, and then I'm just going to hit the U key. So now I've got my SOP solver here, so I can play around with animation, and then over here I can mess around with what I want to do in my sim. So other things that we could do would be maybe we want to not only do we want this sphere to activate these particles, but maybe we want this sphere to like maybe act like a force field or a suction. So what I'll do is maybe I'll create an attractor up here. So if I've got a pop attract, which we used in a previous example, I just plug that into the post solve input on the rigid body solver. Pop attract is set to a goal position of 0 by default. So let's just play that back and see what happens. We should be activating our pieces, and then they should be kind of trying to migrate to the center of the scene. It doesn't look like the force is very strong. Maybe I'll kill gravity just so we can see the effects of it. So I've activated those pieces. You can see they're kind of moving, but the force isn't very strong, but they're sort of starting to move towards the center of the scene. I think what I could do is maybe just increase this force. So on the pop attractor, go to force, maybe just increase the force scale a little bit and see if that makes any difference. So now you can see that those points, as we activate them, they're kind of chunking up and, being attracted towards the center of the scene, which is kind of cool. So maybe what would be kind of neat is if this sphere animation actually served as sort of like a suction. So it's actually trying, as the sphere goes by, it's actually kind of scooping up the particles and trying to attract them to the sphere at the same time. So maybe what I'll do is over here in the pop attract, I could actually see how this, I've got this this transform position that we're using. Since our sphere is set at since we left our sphere at the origin, I could basically just copy the relative references from this transforms position and use that to drive the position of the pop attract. So let's go and right click on the transform for the pop attract, and I'll say copy parameter, and then go over here to the pop attract, and then where it says goal, this is the goal position, I'll just hit paste relative references. And now you can see that handle has jumped to the center of the sphere. So now if I were to play this along, you can see that those pieces are getting sucked towards the sphere, which is kind of interesting. And I might even do something like increase the attraction force a little bit. Maybe we'll bring that up to like 20, and just to make it like attract a little bit tighter. Yeah, that's really kind of scooping all those pieces up towards that sphere. You know, it might be kind of cool is like if we just kind of suck these pieces up. Maybe now we could do a thing where we we suck all those pieces up and then we lift them up and then just throw them down at the ground really quickly. So I think in order to do that, I'll just add a ground plane as a collision now. So you can see that it's kind of plopped it down right in the middle of everything. I'm just going to hit the L key to lay out the .NET again. You can see that our ground plane is over here. It's being merged in so that it collides with our initial setup. So now nothing should go below the ground plane. If I go back and hit play, it is sucking these pieces up. They're kind of rolling together and forming a big pile. So what I'm going to do right now is I'm going to just deactivate this little brain icon so that it isn't trying to update the simulation while I'm setting keyframes. Sometimes when you have these, when you have the simulation enabled and you're scrubbing through your timeline, it'll start to try and recache or resim when you're setting keyframes and changing values in the sim. So I'm just going to deactivate that temporarily, and it won't try and update anything. So now I can go set my keyframes and it should be fine. So I'm going to select the transform. I'm going to go over here next to my geometry spreadsheet. I'm just going to add the animation editor. So now I've got my curve here that, you know, illustrates that sphere moving from left to right. And then let's maybe pick it up a little bit. So I'm going to just have it maybe jump up to frame 120. Now it looks like now that we're going to be adding animation to the X and Y axis, I'm going to just go back to frame 0. I'm just going to option click the translate field just so I get keyframes for all the channels, and then maybe I'll click this little button to go to the next keyframe, and then I'll just hit another keyframe there. That way I know that it's going to keep those translations on the Y and Z axis at 0 and constant up until frame 72, and now I can start animating as usual. So I'll bring this up. Maybe we'll just have it kind of float up into the air like that by frame 120. I'm just going to option click again. So now we've got our animation going out and then up, and then we'll just have it slam down into the ground like that, and I'll just have it go a little bit below the ground like so, and hit another key, and we should be good. So here I think so this is the general motion of our animation. There'll be a little bit of lag in it, so really like what are we saying, really non-finessed keyframes are probably going to end up looking pretty cool, just because they're going to be still, because we're not going to see the sphere in the end unless you want the sphere to be part of your animation. Maybe it serves as like a sort of aura force field or something like that. Really, these particles are going to be lagging around and just be using forces to kind of track to the sphere. But just for the sake of making things look a little bit cooler, I'm going to kind of pull some of these values around. So I'm going to select these keys on frame 120, and I just want to give it a little bit of like hang time. So if I hold down, if I grab these and hold down the control key and just kind of drag them out, you can see they keep the same slope, but they it just allows me to pull that tangent along its I guess, along in a direction that is tangent to wherever it is. So I'm going to grab this one. I don't want this one selected, so I'm just going to grab this first one, and then these guys. I'll pull them back a little bit so it kind of goes up and then slams down. And I think in this Y motion, I'm going to just increase the slope there, so it just continuously accelerates into the ground like so. And then this tangent is a little bit off to the right. I'm just going to maybe pull that one out. Maybe I'll pull these. Maybe I'll just kind of get these all the same. I'm just going to, let's see. Yeah, I'm just going to, maybe I'll pull this one out a little bit in that direction. And then for our Y and Z, I'll just grab these and pull them off to the side as well. So it goes off to the right, and then up, and then down. Let's just see what that looks like with our simulation now. So I'm going to go back to frame 0, and we're going to turn on the brain, and let's just play this back and see what we get. I'm going to pull this down a little bit too. Oh, and it looks like it's not simulating because I'm inside this SOP network, and we want to be inside of this network to actually get it to do anything. You can see it's starting to cook it. It's starting to cook it out. I want to see that playback in real time. I'm just going to hit escape, go back to frame 0, and click play. So it's simulating. Now you can see it's caught up. It's lifting up those particles. They're flying up in the air, and now they're coming slamming down into the ground. And then when they get there, they kind of bundle up and turn into a pile. So let's just play that down a little bit. Let's do this. So I'm going to turn on hide other objects just so I can kind of focus on this. So sphere comes through, picks up those pieces, they fly up in the air and then slam down into the ground, but they're still sort of being attracted to that central location. And I think maybe they go up a little bit too high. If I just throw down my sphere, it looks like, yeah, the sphere comes flying up and they go blasting into the air behind it. You could use drag forces to try and even some of that out, but you know, it's just, maybe I'll do that. I'll just add a little drag in there. So let's throw on a drag, pop drag, throw that underneath the pop attract, and let's see what this gets us. These pieces are being attracted up to frame 72, then they're being lifted into the air. And I can already tell that this is probably a little bit too much drag, but you can see how they don't go quite so high into the air. Maybe I'll just reduce that pop drag to like 0.1. Just reduce the air resistance so that it doesn't quite slow it down so much. And let's just play that back. And they're being picked up into the air and slammed into the ground. I mean, that's cool and all. I actually kind of like the aggressive nature of how it looked without the pop drag, so I think I'm just going to turn it off. And then what I'll do is I'm just going to play this back one more time. I think maybe what the answer is just maybe not making this go so high once it gets to this point. I'm just going to bring that y-axis down a little bit, and you can see that it's modifying the curve down here just because I'm on a frame and I'm adjusting it. So let's just go like something like that, and I'll go back to frame 0 and make sure I've got my sim selected and click play. All those chunks are getting sucked up, and then they're going to get pulled up like so and slammed into the ground at about frame, looks like. So what I'm going to do is just kind of time this up. I'm just going to do this by hand. At about frame 156, they start making contact with the ground. So I'm going to just deactivate my pop attract at that point, and it should make it so that all these pieces are moving relatively quickly towards the ground, and they should all sort of start to react accordingly. So I'll just actually, at that point, I want this pop attract to stop. So I've got this activation right here. It's at frame 157. I can just set a keyframe there. So this is activated up until frame 157. Set a keyframe, move forward a frame, and then I'll just turn the activation off, and then Alt click again in the activation to set another keyframe. So that force is now being turned off at frame 157. So let's play that back. See, the attraction is sucking up those particles, or those pieces, lifting them into the air, beginning to slam them down, and then it will stop attracting at some point. And you can see that they start to fly off in all different directions. Now, we never turned gravity back on, so I think what I might do is reintroduce gravity, and I'll probably have to change some of these force amounts to get it to behave well with gravity, because I'd like these pieces to come slam down on the ground and then sort of react to gravity afterwards. So let's see what we get when we turn gravity on. And I can already tell that that gravity is actually overcoming, for the most part, those forces, and only until it starts lifting up into the air and then coming back down like so. So I think what I'll do is I will actually increase this pop attract force some more. Let's just bring it up to something like 50 and see what happens. I really want to maintain that sort of ball that forms over here as those pieces are being sucked up. So that's happening. That's good. Then it lifts up into the air like so, and then gets slammed into the ground. But something weird was happening there. It looks like it came up and then started to fall down, because it looks like maybe gravity was continuing to overcome that force. So I'm going to actually bring, now I'm going to go back on my word and bring this this sphere up a little bit higher, just so it has like a little bit more lift on it, so I can see better what's going on. So go back to frame 0, make sure I've got a node over in my sim selected, and let's play that back a little bit. So it comes, sucks up all those pieces. Sphere should be moving up into the air now. And it should be coming back down towards the ground now. Cool. And it looks like I just need to adjust when my keyframe that deactivates the attractor occurs. So let's see, we go up here, and I think that right around this frame 142 is where that contact happens. So I'll just go up to the pop attract. And I've got this activation on here. Let's see the activation. I want to right click channels and add to channel list. Sorry, not add to channel list. Oh, I have a filter on down here. I'm going to turn that off. I was filtering different types of keyframes. You can filter your translate, rotate, scale keyframes, and just turn that filter off. So if I shift left click on activation, it should scope that into our curve editor here. I'm just going to grab these two keyframes and select the vertical bar, drag them back to 42 so that they release at about this frame. And then they should go blasting off in all directions. So let's just sim that one more time. I'm going to go back to frame 0, click play. And it's not quite as dramatic as I was hoping. I was hoping it would just kind of smash into a bunch of directions. I'm not seeing that force. So I kind of feel like it's moving pretty fast by the time it gets to like right here. So I think if I actually release the force a little bit early, it might look a little bit cooler. So let's just bring this back a little bit closer. So we're actually going to be releasing the force of that attraction. And letting gravity do kind of the, letting the inertia that it had, objects being in motion, wanting to stay in motion, let that inertia and the force of gravity kind of take care of it after this point. Let's go back. Sim again. I said one more time, I would sim this one more time, probably 50 times. So I'm just going to say again from now on, or at least I'm going to try to. Cool. So we suck up those pieces like so, get lifted in the air, and then they smash into the ground. I just want to get a little bit more aggressive with it. I think I'll go over here. I mean, this is just me having fun at this point. I'm just going to make this movement a little bit quicker. I'm going to maybe bring it down in the Y axis a little bit, just to have it so it maybe doesn't go quite up so high. I don't know. I kind of liked where it was going before. Let's just go something like that. Just play this down, see what we get. This is what it is. A lot of sims just trying different things, watching it play out, trying something else, watch it play out until you get a look that you like, you know? That's getting there. That's cool. I'm liking how these pieces are flying off to the side. Now we've got a different moment of contact yet again. So here, I think if I look at our pop attract, it's actually, if we go to the activation key, it's actually, I need to move this back a little bit. So I'm just going to grab it and grab a vertical bar, move it back to something like, where were we? Something like right about here. And let's just grab those. I don't think I need this key. That's just a spare one that got thrown in there on accident. Grab these guys and let's just move this back like so. And let's see what we get now. I think that I really don't need as much hang time. Now I'm looking at this. I don't really want it to do this kind of easing down. I actually want this to just plummet into the ground. So I'm just making this happen. At frame 120, it goes up, and then I want that attraction to just slam it into the ground over just so you see that sphere moving. It just goes straight down really quickly. So that attraction should get pretty crazy. I also don't think that it needs to linger so much over here before it goes up. I'm gonna let's just decrease the amount of time that this whole thing takes a little bit. So I'm just gonna grab all these keys and just sort of grab one of the vertical bars and move them in like so, and see what that does. That's kind of just cutting a second off of its whole scooping the particles up section. And let's play that back. And it's not updating the sim because I'm again over here in the SOP. I have the SOP solver selected, so I'm going to go back over here, and now we'll resim. Cool. And it makes contact around frame 110 now, so let's move this attractor. Keyframes just to right before that. I think also before I really get carried away with that, I want to also increase the force of the attraction. I'm going to just double it. Let's go up to a force of 100, see if we can make this thing look even more aggressive. So it's sucking up those pieces. It moves over. That's cool. And then it lifts up into the air like so. And then it plummets into the ground like really fast. And then it starts to, and then it stays clustered down there. I'm almost thinking I'll go, as it starts to go into the ground, I'm going to just increase this force scale to something much higher. So I'm going to just set a keyframe on force scale. I'm just going to alt click that. We'll move forward a couple frames, like maybe to like right here. We'll move that forward, and then I'm going to increase this to 1,000. And see what that does. So my force is just getting, my force remains, if I go and frame up those keys, my force remains constant up until about the time when it starts to slam down, and then it gets really strong. So let's play that down. I didn't want it to get too I don't want it to get too strong for this part because I kind of like the lagginess of it that it had. But now I can tell that it's actually really just pulling that into the ground very, very rapidly. So actually, maybe what I'll do is let's decrease this force, the initial force, a little bit more. So I'm just gonna hit the brain here. I'm gonna bring this down to, let's just bring it back to around 50. Oh, not 500. Let's bring it back to 50 here, and then let's see what happened when it hits the ground now at about frame. We can say at about frame 103, we can release it. So let's just bring this keyframe back to frame. We're going to bring the ending keyframe back to 102. So on the pop attract, the activation, on frame 103 it's off, and on frame 102 it's on. I hope that's enough. I don't know if it's accelerating fast enough for that. I might actually just delay this one more frame. Let's go like that. Like so. Yeah. All right. And then let's go back to frame 0. I'm going to turn my brain back on, and we'll click. You can see it because we made, yeah. So it looked like it didn't update that it needed this to redo this cache. Sometimes if it thinks that it still has, that nothing's changed, what you can do is just turn off a node and then turn it back on somewhere in your .NET, and then it outdates the cache and will allow you to resim. So let's just do that. So we got this nice laggy, kind of drifty attraction with these pieces. They get lifted into the air. I like how it has some of these trailing pieces behind, and then it gets slammed into the ground. And that's what I was after, is that sort of explosion where all those pieces go flying off in a bunch of different directions. So this is sort of, I mean, this may have seemed a little bit tedious, but really I think, you know, part of being like, part of like doing impactful and you know, cool looking sims is actually, you know, motion designing them. Still, you still want to make sure that they have the right impacts when they have them, and a lot of that you can see through this process is a lot like you're actually keyframing forces instead of keyframing positions. I mean, we're doing some vague position keyframing, but we're not really polishing these positions too much. But we're really trying to polish is like how much these forces are pulling things along to get these nice aggressive sort of slamming actions and stuff like that. So it's something that takes a little bit of practice, but you can get used to it after a while and start to like figure out different ways where you can use forces as your means of animation instead of traditional keyframes, because that's really what simulation is all about. It's really more about how different forces are interacting with one another. So if I play this down, you can see we're sucking up all those pieces. They get lifted into the air and then slammed into the ground really aggressively. I just want to turn off the handles so that we're not being distracted by those. So I'm going to just maybe hit my selection mouse button up here. I'm just going to hit Control B so that we can just sort of focus on the sim itself and just play that back. And maybe what I'll do is I'll actually flipbook this. So we'll just hit start and just watch as it makes a nice little flipbook for us. A flipbook kind of can take a couple seconds to get started as it's opening up mplay, which is here. And you can see it's going through, picking up those pieces and slamming them into the ground and getting that nice explosion type of effect that we're after. And all our pieces are flying off, and you can see our ground plane truly does extend into infinity. It's, even though you're not seeing the ground plane right there, it is doing its thing, but so this is it in real time. Grab the pieces and slams into the ground. So really that's kind of, that's just fun. We sucked up all these pieces by activating them, by having it follow that animator. And then we were dialing up the forces to get it to behave in certain ways. But you can do all sorts of things like, see, you notice how when it lifts up, we've got these trailing pieces that sort of follow behind. And then we keyframe the forces off. It's just a really fun and different way to animate, where you're really more or less pushing around physical properties as opposed to just positions and rotations and scales as you would do with like a normal like traditional animation. So that's a cool example about how we can activate RBDs. Just a quick note that I wanted to make about this setup that I forgot to address earlier is if I go back here to this section, you can see I've got it. We're doing our simulation here. We're sucking up our particles, lifting them up, and slamming them down. Suppose you wanted to do a slightly different animation. Suppose you wanted it to go, just start in the center and move to the left or something like that. I'm just going to go into my transform here and maybe just move this first keyframe. I'm just going to grab my transform and move it. Maybe let's just say we want it to start over here, for example. So I'm going to do that and go back over to my sim and let's play that back. Well, you can see that it's following here, but it's still pulling particles from this section over here. Like our sphere isn't there. If I throw our attractor here, you can see that it's actually still activating that initial region. That's because back over here where we create our floor, I forgot to turn off this little thing that we did over here, which was it's initially actually still activating that little position where we put this sphere. So if you run into some issue like that, you basically just, when I copied this section into our SOP solver over here, I forgot to deactivate it over here. So basically what I want is everything to be deactivated by default, and I don't need any of this to happen. So I'm just going to turn that off. Now if I go back, and then I'll just go back over to my sim, now that little section that we initially had set up will have all of its active attributes set to 0, and it shouldn't be an issue anymore. So now we're just moving over here and activating those particles and lifting them up, or activating those pieces, lifting them up, and then slamming them down. So just a little quick note about a thing that I missed, and hopefully it didn't trip you up too bad, but so there's that as well. And I will catch you in the next lesson.